Welcome to CS3308 Information Retrieval. This is the Unit 3 lecture part 3. During this lecture, we're going to finish the conversation that we've had and started in the first two lectures. First of all, talking about the need for compression because of the storage problem. We talked a little bit about the speed of memory and the fact that disk is dramatically slower than memory, so we want to try to keep things as small as possible, particularly with the dictionary, to keep it in memory. We then talked a little bit about the need to, and some strategies around keeping that size small, particularly in the dictionary list, by using some techniques such as, instead of using fixed width terms in a fixed width structure, trying to use some form of a maybe dictionary as a string, using a set of pointers, so we create linked lists, and that allows us to have variable size terms, and the fact that that can actually reduce the amount of storage that we have. Now, what we're going to move into talking about now, just briefly, is what do we need to do in the postings side of the equation. So we know that we have a dictionary, and the dictionary has a pointer to a postings file. And what's in that postings file, or that postings list, is for any particular term, I'm going to have a whole series of numbers in there, and what those numbers are going to do is they're going to refer back to a document. So maybe the document is, mytext.txt, and it has, an article that I wrote in there, right? Well, I'm going to assign a number to that document. And the way that the postings file works is that I'm going to put that document number in there and associate it with the term. So for every single term in the document, and maybe there's 5,000 different unique words in my document. If I have 5,000 unique words in my document, then each of those 5,000 words has to have an entry in its associated postings list that includes the document ID of my document. Now, that becomes a bit of a problem if you think about it, because that means for every single word potentially, and again, words tend to get repeated, but essentially I have to have an entry for every word that appears in a document, relating it back to the document. Now, if you think about this for a moment and you start thinking about the Reuters corpus, for example, that has hundreds of thousands of documents in it, that becomes very significant. It means that our posting files can grow to be quite large. Now, essentially what we know about this is that the posting files, when I look at it in relationship to the dictionary, it's large. So we know it's going to be much larger, at least a factor of 10. So if my dictionary has 5,000, or let's say my dictionary is, it's 10 megabytes, right? Then we know that the postings file is going to be at least 10 times that, meaning it's going to be 100 megabytes. So we see the relationship that exists between the dictionary and the postings file, and the postings file is going to be dramatically bigger. Now, in the previous unit, we kind of covered this whole concept of Hadoop, and the fact that we use Hadoop because of its immense parallelization, because of the fact that I can split this stuff up to process it. And hopefully by now you're starting to get a sense of why we need to do that with a technology such as Hadoop, because there is so many terms in so many documents in many cases to go out and index a corpus that it can take a very long time, because essentially what I'm doing is I'm saying I'm going to go find what postings, or every time a word appears, I got to go find that word, and I have to add the document to the end of its posting list. That can take a long time, because quite frankly it's going to process millions of them. So essentially very large posting files get very large. Okay, one of the things we want to do, and the thing that we desire to do, and again we've already talked about why, is try to store this data compactly. Okay, we talked about compression. We talked about trying to use variable sizes to eliminate waste. We talked about the fact that I want to minimize the amount of space or the amount of reading on disks that I want to do, because disks are slow. So essentially our desire is to store every single post as compactly as possible. Now let's talk about that and look at this for a moment. So let's think about the Reuters. Assume we have 800,000 documents. How do I store an item number that refers to one of 800,000? Or, perhaps one of 8 million? Or even 8 billion? It becomes a bit of an issue. So, one of the challenges that we have is if I'm having to use, a long integer number to do that, okay, I wind up, consuming 4 bytes. So one of the strategies we can look at is looking at how many bits are required to represent that. So if I look at, log 2 of 800,000, it basically is going to tell me that I have roughly 20 bits. So essentially our strategy is to say, how do I and what do I do to kind of get to this number where I'm reducing the number of bits. So for example, long integer is 32. I really need something closer to 20. That means there are 12 bits of information that I'm wasting for every document. And again, it's the same kind of a problem that we had with the fixed size in the dictionary, right? In this case, the fixed size is the fact that I'm using 4-byte integers. So one of the strategies is to use bitmaps, even in some cases, so that we can bitmap onto fewer bytes so that I can come up with a way of posting this. And sometimes the way that I have to do that is that I don't align my data across normal data type boundaries. So often what we're going to wind up doing is we're going to create structures where I might take a normal data type, maybe a data type of a char, right? Because I know a char has exactly 1 byte, right? And map onto that. So maybe I take a character with 3. So if I had 3 bytes, that means it's 24 bits. And I lay on top of that 24 bits my bit-mapped representation of the document ID. Essentially what I just did is I said, okay, I'm going to make it a little bit more complex. I'm going to have a little more processing to try to represent that document ID, because instead of just using the integer and keeping it simple, I might want to go create a bitmap of the image so that I'm going from the 32 bits down to 24. And I'm saving myself an entire byte for every single one of those posting files. Okay, that means I just got rid of 25% of the space. Again, this is a great example of us trading computational complexity or more processing overhead, like for example to create the bitmap image. But the advantages that we get is that we're using dramatically less space. And in fact, my simple example of 24 bits, we can employ other techniques, and I'm not going to go into some of those techniques here because they're a little too complex and take us too much time. But I can actually employ other techniques to dramatically reduce this even further. I might do things such as segmenting the data, right? So maybe a portion of what the information that's in this 24 bits I can actually achieve by maybe segmenting it into groups, right? And so, as long as I get to the right group, I don't need as much information in that posting list. Maybe I say I have the A group and the B group and the C group and the D group and so on. But again, thinking about those kinds of strategies to dramatically reduce the amount of space that the posting files are using. So again, concluding the third of the 3 lectures, what we've been really covering here is all about how do I minimize the amount of space, how do I make it more efficient, how do I reduce the amount of space that I'm consuming. And it's not as important for the small corpus that we're using, which is 1.5 megabytes. But as we start getting up to enterprise scale, when we start looking at internet scale, this becomes extremely important. And in fact, a lot of what we're going to do as professionals working with information retrieval systems is really trying to come up with more sophisticated ways of doing more with less, trading off computational capability which is fast, for disk, which is slow, and things of that nature.